Hi everyone, I'm Dan Fullerton, and I'd like to welcome you back to Educator.com as we continue our study of thermal physics and thermodynamics by talking about ideal gases. Now, our objectives for this lesson are going to be utilizing the ideal gas law to solve for pressure, volume, temperature, and quantity of an ideal gas, and explaining the relationship between root mean square velocity and the temperature of a gas. So with that, let's talk about ideal gases. Ideal gases are theoretical models of real gases which utilize a number of basic assumptions to simplify their study. The first assumption is that the gas is comprised of many particles moving randomly in a container. 1-2 molecules in a container isn't really a good model. We've got to have some substantial amount of gas. The particles are on average far apart from one another. They're not all combined almost in a liquid state. And the particles do not exert forces upon one another unless they come in contact in an elastic collision. So we're going to neglect things like the gravitational force of attraction between these tiny particles. Now, this works well for most gases at standard temperatures and pressures, but it doesn't hold up so well for very heavy gases at low temperatures or very high pressures. But for most of the things we would want to use it for, it works just great. So, the ideal gas law relates pressure, volume, number of particles, and temperature of an ideal gas in a single equation. And you can see this written in a number of different forms. Pressure times volume equals nRT, PV equals nRT, or capital N K sub BT, depending on how you want to see it written. And we'll talk about what these different values are. Now, N, the number of moles of a gas, little n, is capital N, which is the number of molecules divided by Avogadro's number, or 6.02 times 10 to the 23rd somethings per mole. So, in this equation, pressure, capital P, is given in pascals. The volume, V, is in cubic meters. If you use little n, that's the number of moles of a gas. We use that over here. R then is the universal gas constant, or 8.31 joules per mole Kelvin. Use that if we're using the number of moles of a gas version, and T is the temperature in kelvins. On the other hand, if you want to use this version, PV equals NKBT, where capital N is the number of molecules that you have. KB is Boltzmann's constant. We talked about that previously, 1.38 times 10 to the minus 23rd joules per Kelvin. And T, again, is your temperature in kelvins. Now, before we move on, it's probably important to note that 1 mole of a gas at standard temperature and pressure has a volume of just about 24 liters. That's always a good thing just to have in the back of your mind. All right, atoms, molecules, and moles. Atoms are made up of protons, and we'll call the number of protons the Z number. So when we write something like a molecule or an atom, X is the symbol for it. Z is the number of protons. Goes down here to the bottom and to the left of the element. N, the number of neutrons. They don't have any charge. And if neutral, you have Z electrons. You have 1 electron with the charge of -1 elementary charge for every proton. Now the atomic number up here, the atomic mass, A, is the number of protons plus neutrons. So you've got the protons here, you've got the protons plus neutrons here. So if you want just the number of neutrons, take A, subtract Z, and you'll be left with the number of neutrons you have for your atom, molecule, element. Here we have 2 for helium. That means that we have 2 protons. We have 4 protons and neutrons, which means we must have 2 neutrons. And 1 mole of helium is approximately 4 grams. Here we have carbon-14. The 6 tells you that it has 6 protons. The 14 means it has 6 protons and neutrons, therefore we must have 8 neutrons. And 1 mole of this material has a mass of about 14 grams. And if we looked at something like oxygen, that has 8 protons, 8 neutrons, and if we looked at 1 mole of molecular oxygen, O2, it's going to have a mass of about 32 grams because it's O2. We've got 2 of them there. And that's going to have 6.02 times 10 to the 23rd molecules. All right, so let's see how we can put some of this together. How many moles of an ideal gas are equivalent to 3.01 times 10 to the 24th molecules? Well, let's start with 3.01 times 10 to the 24 molecules. And I'm going to multiply that by 1 mole over 6.02 times 10 to the 23 molecules in a mole, Avogadro's number. And really what I'm doing is multiplying by 1. And anything I multiply by 1, I get the same value even if the units are changing. 1 mole and 6.02 times 10 to the 23 molecules are really the same thing. So 1 over 1 is 1. However, when I do this multiplication, my molecules will cancel out and I'll be left with units of moles. 3.01 times 10 to the 24 times 1 divided by 6.02 times 10 to the 23 gives me 5 moles. Let's look at another example. Moles of carbon dioxide in a bottle. How many moles of gas are present in a 0.3 cubic meter bottle of carbon dioxide held at a temperature of 320 K and a pressure of 1 million pascals? We'll use our ideal gas law, PV equals nRT. Therefore, N, the number of moles, is going to be equal to PV over RT, where our pressure is 1 million, or 10 to the 6 pascals. Our volume is 0.3 cubic meters. R, our universal gas constant, is 8.31, and our temperature is 320 K. Gives me about 113 moles. All right, let's take a look at another example, pressurized carbon dioxide. We have a cubic meter of carbon dioxide gas at room temperature, 300 K, and atmospheric pressure, about 101,325 pascals. It's compressed into a volume of 0.1 cubic meter and held at a temperature of 260 K. What's the pressure of this compressed carbon dioxide? Well, since the number of moles of gas is a constant here, we can simplify the ideal gas equation into some combined gas law by setting the initial pressure, volume, and temperature relationship equal to the final pressure, volume, and temperature relationship. So, if PV equals nRT, and we're holding N and R constant, I could pull T over to this side, PV over T equals NR. NR must be constant, so I could write this as P1 V1 over T1 must equal P2 V2 over T2. And since I want pressure 2, I can rearrange that to say that pressure 2 equals P1 V1 T2 divided by T1 and V2. Now I can substitute in my values. Pressure 2 equals, well, pressure 1 is 101,325 pascals. Volume 1 was 1 cubic meter. Temperature 2 was 260 K. Divided by temperature 1, that was 300 K. And volume 2 is 0.1 cubic meters. When I do this, I come out with a pressure 2, or a final pressure of about 878,000 pascals. Let's look at a helium balloon. 1 mole of helium gas is placed inside a balloon. What is the pressure, looking for pressure, inside the balloon when the balloon rises to a point in the atmosphere where the temperature is minus 12 degrees C and the volume of the balloon is 0.25 cubic meters? First thing, let's convert this temperature from Celsius to kelvins. Temperature in Kelvin is our temperature in degrees Celsius plus 273.15. So that's going to be negative 12 degrees Celsius plus 273.15, or 261.15 K. Now, if PV equals nRT, then pressure equals nRT over V. Well, N, 1 mole, R, the gas constant, 8.31, our temperature, 261.15 K, and our volume here, 0.25 cubic meters, gives us a pressure of about 8,680 pascals. All right, as we talk about the internal energy of an ideal gas, recall that the average kinetic energy of the particles is described by the equation average kinetic energy is 3/2 times Boltzmann's constant times the temperature in kelvins. Now, the total internal energy of the ideal gas can then be found by multiplying the average kinetic energy of the gas's particles by the number of particles. So, the total internal energy, U, is going to be the number of particles, capital N, times the average kinetic energy. But we can do a little bit of manipulation here. The total number of atoms, particles, N, is going to be equal to the number of moles times Avogadro's number, and the average kinetic energy is 3/2 kBT. So when I substitute those into my equation, the total internal energy is going to be equal to 3/2 times number of moles, Avogadro's number, times Boltzmann's constant, times the temperature. This implies then, however, Avogadro's number times Boltzmann's constant is that universal gas constant, R. So I'm going to take that and replace it with R to write that the total internal energy, U, is 3/2 N. Now I can place my R in there, nRT. I have a formula for the total internal energy of an ideal gas. Let's see how we can use that. Find the internal energy of 5 moles of oxygen at a temperature of 300 kelvins. U equals 3/2 nRT. So that's 3/2 times 5 moles times our ideal gas constant, our universal gas constant, 8.31, times 300 K, or about 18,700 joules, or 18.7 kilojoules. Let's do another one. What is the temperature of 20 moles of argon with a total internal energy of 100 kilojoules? Well, total internal energy U is 3/2 N capital RT. Therefore, temperature equals 2 times the total internal energy divided by 3 times the number of moles times that universal gas constant R. So that's 2 times 100 kilojoules, or 100,000 joules, divided by 3 times 20 moles times our universal gas constant, 8.31, which gives me about 401 Kelvin. Great. Let's look a little bit more at the velocity of these particles. The root mean square velocity, or RMS velocity, is the square root of the average velocity squared for all the molecules in the system. You can kind of think of it as a sort of average velocity for molecules when we're using this Maxwell-Boltzmann distribution statistics, probabilistic statistics. What we have down here is we've got a plot of number of atoms or molecules, number of particles with some specific velocity for different materials at about 293.15 K, closing in on room temperature. By the way, that's C4H10, that's butane. And you can see that we have different spreads here. For butane, we have a peak here at something just shy of 300 meters per second. So that's where you're going to have the most particles, but you've got a fairly tight distribution around that. As we go to something like ammonia, NH3, we've got a much wider distribution and a greater tail down here at the higher velocities. So just an idea, giving you a feel for what root mean square velocity is and what it means. calculating the root mean square velocity. We're going to start with the average kinetic energy as 3/2 times Boltzmann's constant times the temperature in kelvins. What this means then is average kinetic energy is we're taking the average of 1/2 mv squared for all those particles, and that's equal to 3/2 times Boltzmann constant times the temperature T. But the mass of these particles is constant, so taking the average of it, we can pull the m out of the average and multiply it when we're done. And so can the 1/2. That's a constant too. So that implies if we pull the m over 2 out, that m over 2 times the average of v squared equals 3/2 kb t. Or, if I divide both sides by m over 2, or think of it as multiplying both sides by 2 over m, the left-hand side is just going to be the average of v squared, and the right-hand side, we're going to have 3 over m, Boltzmann's constant, times t. If I take the square root of both sides, well, this is the definition of the average of the VRMS, the root mean square velocity. So VRMS equals the square root of 3 over m kb times t. But this m, the mass, we can give another symbol that's often used. M is often written as the mass of the molecule is written as mu. So I could write VRMS as equal to 3 kb t over mu square root. There's another equation for the root mean square velocity. But we can take that even further. If we start with the root mean square velocity equal to the square root of 3 kbt over mu, this implies then, knowing that Boltzmann's constant, Kb, is actually R over Avogadro's number, Na, that we could write VRMS, or root mean square velocity, as equal to the square root of 3. Now we've got our R over Na right there. We still have our mu down here, and we still have our t. So we've got 3RT over mu times Na. But even more. Mu times Na, the mass of our molecules times Avogadro's number, is going to give us what's known as the molar mass, capital M in kilograms per mole. So a little bit more we can do here. We could write this then as VRMS equals the square root of 3 RT over the molar mass M. Another version for calculating the root mean square velocity. Let's take a look at an example here. An ideal gas is placed in a closed bottle and cooled to half its original temperature. What happens to the average speed of the molecules? Well, the root mean square velocity is the square root of 3 RT over M. And we're going to cut T in half. Everything else is going to stay the same, but if we cut T in half and VRMS is proportional to, well, that's going to be, if T is 1/2 what it was, that's going to be proportional to square root of 1/2 what we had for its original velocity. Square root of 1/2 is about 0.71, so it's going to be 0.71 of its original velocity. Or you could write this as the average speed, if we think of it in terms of average speed, is going to be about 71% its original value. Take its original value multiplied by 0.71. Let's do another one. These can be a little bit tricky when you see them the first time. The root mean square velocity of the molecules of a 300 K gas is 1,000 meters per second. What is the root mean square velocity of the molecules at 600 K? Well, again, we'll start with V RMS equal to the square root of 3 RT over the molar mass M. Now we're going to double the temperature. And when we double the temperature, it's proportional to the square root of T. So VRMS is proportional to the square root of 2 times the original RMS velocity. So that's going to be square root of 2 times 1,000 meters per second, or VRMS is 1.41 V original, which is 1410 meters per second. You get a 41% increase in the root mean square velocity of the molecules when you double the temperature. All right, trying another one. Hydrogen, H2, and nitrogen, N2, gas are in thermal equilibrium in a closed box. Compare the root mean square velocities of the molecules. Well, we're going to start by referencing our VRMS equation is equal to the square root of 3RT divided by M. Now the molar mass of hydrogen is 2. The molar mass of nitrogen is 28. That means we have a 14 times difference. All right, so when I look at what these are proportional to, it's 1 over the molar mass. So if I were to take a ratio of these two, on the top I'd have the square root of 1 over 2, because we have 2 for the molar mass of hydrogen, compared to 1 over the square root of 28 for my ratio for nitrogen, which is going to give me an X factor of 3.74. That means the root mean square velocity for hydrogen is going to be 3.74 times larger than the root mean square velocity for nitrogen. As to be expected, it's a lot smaller. Find the number of molecules in 0.4 moles of an ideal gas. All right, a conversion problem. 0.4 moles, and we want to convert this into molecules. All right, so I'm going to multiply. I want moles to go away, so I'll put that in the denominator so they make a ratio of 1 and cancel out. I want molecules as my unit, and now I need to make sure I'm multiplying by a value of 1. 1 mole is equal to 6.02 times 10 to the 23 molecules. My moles, units, will make a ratio of 1 or cancel out, and I'll be left with 0.4 times 6.02 times 10 to the 23 molecules, which is 2.4 times 10 to the 23rd molecules. All right, let's look at one last problem here. The temperature of an ideal gas is doubled. What happens to its internal energy? Okay, first thing I'm going to do is recall that internal energy equation. U equals 3/2 nRT. Now if I double the temperature, all right, if I'm doubling the temperature here, I must be doubling the internal energy. I get double the internal energy. So the short answer, internal energy doubles. All right. Hopefully that gets you a good start on ideal gases. Thank you so much for your time coming to Educator.com. Make it a great day, everyone.